The famous GPT-3 language model would have required 355 years to compute if they had used a single machine to do it. Distributed computing is an important path forward in large machine learning projects, and the more machines involved, the more one is exposed to the possibility of Byzantine fault-tolerance. This is Data Skeptic Consensus, and the 25th installment in our series about how multi-agent systems achieve collective decision-making. Today on the show, I speak with Nirupam Gupta about the recent paper Byzantine Fault-Tolerance in Peer-to-Peer Distributed Gradient Descent.
Hello, everyone. My name is Nirupam Gupta, and I am a computer scientist working as a postdoctoral researcher at EDFL University in Switzerland. I work on distributed computations. Specifically, I work on algorithms concerning distributed optimization, distributed consensus, and distributed collaborations in systems like swarm robotics and online votings. And in this particular area of research, I mainly focus on fault tolerance, Byzantine fault-tolerance, meaning we consider networks where some of the nodes in the networks are malicious, adversarial, or they are just faulty. And how does this affect the overall computation of the algorithm?
Now, this is something that's interesting to me in my engineering part of the brain. You know, if I was working for a big company, I'd say, well, we can control all of our nodes. I mean, I maybe have to worry about some rogue employee or something. But I guess outside of a company, the world really runs on bigger systems. How common are these sort of peer-to-peer distributed problems in people's everyday lives?
Definitely. I mean, for example, just consider our current situation, which is the COVID pandemic. And let's say you have these COVID trackers, right? You have these COVID trackers on your phones and you are carrying these trackers with you. So what these trackers do is whenever you come in close proximity to someone else, let's say who might have contacted COVID or who might in recent history be tested positive. So this app then gives you a notification, hey, you came in contact with this person and he was tested positive. So you may want to, take some precautions. And let's say based on these kind of COVID trackers, companies and government start building policies. Just imagine how difficult it would be if someone starts messing around. For example, let's say people will falsely claim themselves as high risk, saying that, oh, I'm just high risk COVID, so whomever I'm coming in proximity with is also at high risk. That would just create a hell lot of problem, right? So peer-to-peer systems are already there in use. It's just we are naively ignoring the fact that some of the nodes in these systems could be malicious or faulty. Just like internet, you have millions of nodes on internet, and not everything is on a cloud or a server controlled by a big tech or big government administration. There are so many of these nodes that are just spreading misinformation. They are just trying to disrupt the internet. For example, you might have heard of things like jamming attacks, where people jam the servers just by sending queries. So, these kind of nodes are very, very fairly common in our everyday use. It's just we get to hear them when there's a big disaster or when there's an actual breakdown of these systems.
When I started learning about distributed computing, and of course it was called big data at the time, one of the first examples is term frequency. So in a lot of documents calculate, the percentage of times you see something, and that often gets labeled as embarrassingly parallel, because if you just want a frequency, you need the numerator divided by the denominator, and it's easy to divide that problem up and rejoin it. But not every problem is so embarrassingly easy to solve. What about your specific research into gradient descent? What makes that one hard to do in a distributed fashion?
You have this distributed network and you want this network to be useful to the specific problem, let's say, that you are trying to solve. For example, as you just mentioned, either you're trying to get the frequency of a word from documents spread on the internet, or let's take a step forward. Perhaps you are trying to build some kind of image classifier. So different nodes on the internet have different data sets, let's say images of their dogs, and you want to use all these images of dogs, like so many images of dogs, you could build a very, very strong image classifier for dogs, something that would just parallel the human ability to classify a dog. So you want to, let's say, solve this complicated problem. Now, designing an image classifier using all these distributed data set on the internet with different nodes having different data points, it's quite complicated even when you have all the data points at one particular machine. It's a hell lot more complicated when the data sets are divided into different machines. So to ensure now that algorithms like these, like machine learning, run smoothly when certain nodes in the network are malicious, it's just far more challenging. And not just challenging, it's very interesting to study how these algorithms can be run smoothly. Now, gradient descent is one specific algorithm that is by far the most common algorithm used for machine learning these days. And what happens in gradient descent is you have these different data sets distributed on different nodes. Therefore, different nodes will have different loss functions. Now, what we are trying to do now in this distributed setting is minimize the aggregate of all these cost functions or loss functions. Now, when you're doing this, by nature, the most commonly used algorithm is gradient descent because it's naturally distributed. When you apply gradient descent, it just reduces to add the gradients of the different loss functions in each round or iterations of your learning algorithm. Now, when you're adding these gradients together, some nodes are not going to provide you correct gradients of their loss functions. They may be faulty and they may be providing you arbitrarily incorrect gradients, may be designed maliciously in a way to move you towards a solution that favors their particular data points. They may favor, let's say, dogs of a particular breed or some other kind of notions, or maybe they want to completely render the classification problem useless. They want to maybe, instead of dog, will train you to classify horses. So as you can see, ensuring that distributed gradient descent runs smoothly, or at least within some reasonable tolerance in presence of such faulty nodes, is of great practical importance at this point when you have all this learning algorithms training using data sets coming from all sorts of people on internet.
Let's imagine that you and I decide to be the villains of this story, and we're going to go out there and do everything we can to pollute the distributed gradient descent calculations. We'll get into the pool and we'll spit out, nonsense answers or something like that. What do we do to be the most malicious in that scenario? How do we skew this process?
The best thing for us to do is to come together and say, instead of dogs, we are going to send gradients that correspond to horses. So we'll only give you images of horses. We'll hide that data set, obviously, from you. For the rest of the honest people, they will think that our data set is still dogs, but the gradients that we would be sending would correspond to the horse data set. So what happens is, because we are not actually arbitrarily changing the gradients does correspond to a correct data set. Only the correct data set is not dogs, but horses for our case. And so it would appear as if the gradients that we too are sending in the system are correct. However, they're not. So if suppose people like us become even close to the majority of the nodes in the network, like even if, let's say, 40% of us start doing this, there is no possible way for the distributed gradient descent algorithm to actually correctly learn a dog classifier.
And do we need that 40% to be damaging, or could one individual node, what percentage of a network has to be Byzantine before it's really affecting the output?
Well, that is where the interesting part comes in. It's different for different problems. Some image classifiers are more vulnerable, meaning for damaging them, you perhaps only need 20% of the nodes in the network to be faulty. Some other image classifiers maybe are more robust, meaning that to damage them, perhaps you need at least 30% or 40% nodes to be corrupted. And here's one of the interesting mechanisms or techniques against such faulty nodes is to maybe reformulate your problem in a way that it's less vulnerable to such kind of faulty nodes in the network.
It makes sense that there would be some problems that would be more susceptible than others, sort of from a raw mathematical data perspective. But if we step back and looked with our human eyes at that, would we be surprised at which data sets were confusing? Is this going to be cases like the dogs that look like muffins and it's very close? Or is it more like the fooling images cases where it's just at the very low-level tensor calculations?
For example, there are cases where two images look very similar to human eyes, but an image classifier completely misclassifies it because it got fooled during the training process or the learning process. So it could be that to you and me, it's still a dog, but for the neural network that classified it, because of these faulty nodes, is classifying it as horse. So these are not something very apparent because the learning algorithm is not like you and me. It's still in a very nascent stage. And so the learning algorithm gets tricked, not your eyes. So for us, the reality would still be the same. However, the thing is, like, when you are automating so many systems, you won't be able to control the quality of your classifier by putting a human at work saying that, just make sure each and every classification is correct. In most cases, you are only going to rely on what your machine classifies. And there are cases where the image still looks like a dog to any common human being, but the machine is classifying it as horse. And some other images, it's classifying again correctly as dog. So it's just, for the machine, it gets trickier.
Could you define the notion of F-resilience?
So F-resilience is a very special property that we worked on while working on this particular problem of fault tolerance in distributed learning. So as I said, you have these different data points stored at different nodes in the network. What F-resilience tells you is that if you have some correlation between these data points, meaning that, for example, let's say your network has n number of total agents. Now, we say that the problem is F-resilient if these agents were corrupted and you were still able to learn the correct classifier. So if you're still able to learn the correct classifier exactly or with some tolerance, despite the presence of F Byzantine faulty nodes in the network, then your algorithm is F-resilient.
I want to call that the best case scenario. Is that fair?
That is the best case scenario, because what we are saying here is, let's say that you are able to solve the problem correctly despite such up to F's faulty nodes in the network.
So that's a great property I'd like my network to have. How do I achieve it?
And that's when the real problem starts. That's when the research work starts. So you want this particular property for your network. Everyone wants it. No one wants to have like some kind of F-resilience or approximate F-resilience or blah, blah, blah. You want F-resilience, let's say. Now you take your problem at hand, whatever you're trying to do. You take your learning problem at hand and then you study it using this for ensuring F-resilience. So first breakthrough that we were able to show in our work is that F-resilience may not, for the problem in hand that you have, it may not always be possible. It is only possible if you have 2F redundancy in the system. Now, what does this 2F redundancy means? What 2F redundancy means is that out of n nodes in the network, if I were to only use n minus 2F nodes for solving my problem, the solution I would get just by considering the data points with those n minus 2F nodes gives me the correct solution that would equate to the solution I would have got if I were considering all the n nodes in the network. So the property, just to repeat this property again, because it's such an important thing. If you're designing your problem, your network to solve a machine learning problem, make sure there is some redundancy or correlation between the data points distributed amongst nodes. If you have totally independent data points distributed at the nodes, there is no way you can have F-resilience property. So make sure now how to distribute these data points is governed by this condition of 2F redundancy.
Sort of like a contract then. If I can commit to making sure I have independent and identically distributed data, I can achieve F-resiliency?
Yes. Short answer is yes. If everyone is sampling from a pool of data points, and then to F-resiliency is achievable if majority of the nodes in the network are good or honest. If the data is, as you said, independent and identically distributed.
Now, that's an idea that sometimes seems like, oh, it's easy to get. You just shuffled the data and you randomize it and you've achieved IID. But in practice, I don't know if you can always do that in a distributed system. How high of a bar is it to make this requirement?
Exactly. So now we are talking about systems here whose nodes are spread all over the world. Dogs in America look different than dogs, let's say, in Europe. They just do because, people have different preferences. So in America, you'll find one particular kind of pictures of dogs. In Europe, you'll find some other kind of pictures of dogs. So obviously the distribution is never going to be identical for nodes in the network. The trick here is that we are saying that you can still solve this problem. Do not need identical distribution. All you need is 2f redundancy. Now, as I was trying to explain earlier, so what happens in this 2f redundancy, we are saying, okay, your distribution is not identical, cool, we'll work that out. How we will work that out is we are saying that all we need to make sure is that out of these n total nodes in the network, let's give this n a number. Let's say n is equal to 10. Now we are saying out of these 10, and let's say f, which is the possible number of faulty agents, are 2 in this particular case. So we are saying out of these 10 nodes in the network, if we could solve this problem of machine image classification, not by using all these data points of 10 nodes, but only data points held by any n-2f nodes, which is in this particular case 6. F is equal to 2, n is equal to 10. So we are saying we don't need all 10 of you, we only need 6 of you. So let's consider again America and Europe. Let's say 5 nodes are in America, 5 nodes are in Europe. So what we are saying is if any 6 of these nodes is solving my problem in some reasonable manner, then I'm good to go. Then I would be able to achieve F resilience. So I do not need identical data sets. All I need is out of these 10 nodes, 5 in America, 5 in Europe, I could take any 6 of them and solve my problem reasonably good, then I'm fine. And that is not far-fetched to assume or to even ensure in systems. You should always, in fact, have certain redundancy when you have these kind of distributed systems. We always have backups for our files. We always have made 2 copies or 3 copies of data of documents that are important to us. So why not have the same kind of notion in such complicated machine learning problems when in near future you are going to rely on such machine learning algorithms for making important decisions. So that's the idea. You can still solve the problem even if the data is not identically distributed.
Earlier, you'd made the comment that gradient descent was the most common machine learning algorithm. If someone is, let's say, early in their machine learning journey, they've probably been working with logistic regression and random forest, maybe the support vector machine or a convolutional neural network. Maybe they've heard of gradient descent, but they don't feel like they've used it. What do they need to learn to understand that it's the most common machine learning algorithm?
Gradient descent, all you need to know to understand gradient descent is flow of water from the top of the mountain to the valley. You know how the ice melts at the top of a snow-capped mountain and the water flows down, reaches the valley, becomes a river. That is exactly what gradient descent does. All it's doing is moving your estimates in the direction of descent. Let's consider this problem of support vector machine. Let's say you want to train this support vector machine for your data. You have some data points and you want to classify them into 2 classes, and you assume this support vector machine model to learn this classifier. You assume, let's say, that your support vector machines have these particular parameters, and let us call those parameters W0. We say W0 is my initial parameter estimate, corresponding to W0 and corresponding to the training set that I have. You will evaluate your loss function. Every learning model has a loss function associated with it. Basically, what the loss function does is quantify the errors that your classifier is making. So you quantify the error incurred at this initial parameter W0. You want to improve this, obviously. What you do is then you compute the partial derivatives of your loss function that corresponds to your SVM model assumed. You compute this derivative, and the nice thing about these derivatives, in vector cases, we call these partial derivatives, gradients. So the nice thing about these gradients is So a gradient is going to be a vector. Your parameter is also a vector. It could be a vector of dimension 100, 1000, depending upon how many parameters you want in your learning model. And the gradient is also going to be a vector of same dimension. Now, the nice property about this gradient is that if you move in a direction opposite to the gradient of your cost function at this point W0, you reduce your loss function. Meaning, let's say you compute your next estimate of parameters to be W1, which is given as W0 minus some factor times the gradient, meaning you are moving opposite to the gradient. So we can guarantee theoretically that your cost function at W1 is going to be less than the cost function at W0. And this, you keep doing this step, the same step, keep repeating it until you reach a parameter at which the loss function is really, really small, or you are satisfied with that particular performance of the parameter. And that's all gradient descent does. It just keeps you moving in the opposite direction of the gradients of your machine learning model's loss function.
Yeah, and if it helps us minimize the loss, it's broadly applicable in every case, really.
Exactly. It's so natural in nature. This algorithm is everywhere.
Right. So given the use not just in machine learning, but broadly beyond that as well, and how appealing it is to possibly parallelize this in the sense that the average of those gradients seems like it would be useful, and in practice does seem to be. I'm sure there's been a history of trying to get gradient descent running at scale. What have been some of the challenges historically leading up to the work you were working on?
It's not always, we just assumed here that we have the gradients in this ideal scenario. It's not always possible to compute the gradients so easily. In practice, it's computationally very expensive. For example, consider a case of machine learning where you have, let's say, 1 million data sets. 1 million data points is not anything big these days, in the age of internet. Obviously, you have 1 million images of dogs on internet. And for computing the correct gradient of your loss function, you would have to compute the gradient corresponding to each one of those 1 million data points in each round, and then keep doing it for multiple rounds so that you can finally converge to a minimum. Now, as you can imagine, doing computing and the modern machine learning models like SVM or neural networks have parameters at least more than 1,000 parameters. So imagine computing this vector of 1,000 dimension for 1 million points. It's like 1 billion multiplication additive operations happening in each particular round. And that takes a huge amount of computation power because these gradients, they're not binary. They're real floating values, and you need to store them and you need to process them. So people came up with a clever idea of saying that, you don't have to compute gradients for all the data points all the time. Just randomly select out of these million, just randomly select maybe 10 of them or 100 of them. Just select them randomly, compute their gradients, and just take the average. And that average is going to be good enough. And what by good enough, what they meant is it's going to be an unbiased estimator of the true gradient that would have required you to compute gradients at all 1 million points. So this particular variant of gradient descent is known as stochastic gradient descent, because you have this stochastic property that you're not computing gradients for all the data points, but only some randomly chosen data points. And that's a very neat trick. In fact, machine learning as we know it today would not have existed without this technique.
How do you see the results of your work impacting adoption in the implementations that are out there? Are there maybe libraries that will start to incorporate some of the insights from your work?
There are companies like Facebook and Google that are already working together with us to design such fault-tolerant algorithms for their machine learning algorithms, because these companies have these massive machine learning models out there, and biggest risk of ending up with a faulty machine learning model if some of the nodes that they are relying on are faulty And let me tell you that if you think that you can control the faultiness of the nodes in the network, that's never going to happen. You have to live with the fact that out of 100 nodes that you are working with, 10 or maybe 5 or maybe even 2 are going to be faulty. And those 2 and those 5 can hugely impact the correctness of your solution if they are malicious, if they are like cleverly designing their attacks. So, as I just mentioned about stochastic gradient descent, so our work originally started with gradient descent, where we were assuming that you can compute all the gradients correctly all the time. Now we are trying to extend this particular work on stochastic gradients, which makes it more practical. So what we have seen is that the 2f redundancy condition doesn't change. That condition is independent of what algorithm you're using. All the stochasticity in the gradients, all it affects is the achievability. Maybe what I mean to say is that perhaps with true gradients, we are able to, let's say, control or tolerate 30% of faulty nodes in the network. With stochastic gradients, maybe that 30% would come down to 20%. But we still would prove or provide you some kind of fault tolerance guarantee. It's going to be much weaker. And I should not say much. It's going to be weaker than what it would be for the ideal scenario, but it is indeed applicable.
I'm curious to hear what you think about the future and how many of us will use some of these techniques. To date, I have to say in my professional life, I've only trained, even when I've trained in a distributed way, it was always a closed garden of servers I controlled. I haven't had yet an opportunity to do something massively distributed. Will that become a more common use case as the technology and tooling becomes better, or is this more of a specialized niche of machine learning?
Well, what I think is going to happen is these kind of fault tolerance mechanisms will automatically be introduced in the learning algorithms, meaning that even if you are using servers that you can control, you would have an option of saying that, oh, you know what, I have 10 servers at my disposal. Perhaps, because they are remotely located, let's say I'm not completely confident about maybe 2 of them. Maybe there could be 2 servers at a time injecting some kind of weird faults in my system. So it's like an insurance policy. You would say, you know what, insure me against these 2 servers that could go bad. They are not, but I just want this insurance. So what would happen is these techniques will always run in the back end of your application. You as a user won't have to deal with it. The algorithm will take care of it. And what the algorithm would do is just use this kind of patch. It just patches the algorithm. It doesn't change it much. It just introduces this robustness feature we call gradient filters or robust gradient aggregation rule. And it doesn't affect your training process or your computation that much. It just gives you this insurance saying that you have been insured against at most 2 faulty servers in your system.
Practically speaking, even if it's minimal, what is the cost of that insurance? Do I have to train a bit longer or spend a few more CPU cycles or what?
Yes, you may have to not train it a bit longer. Your epochs are going to be still the same, but your CPU cycles might increase by a factor that depends on how many nodes you have in the network. So it's linear in n, n being the total nodes in the network. So that's the overhead. So the overhead is linear in n. From my experience, it's not that much because mostly it's the size of the learning model that affects the CPU cycles. Size is the deciding factor of your learning rate. Number of nodes could be 1,000, 10,000, still okay. But the size of the models these days is growing bigger by the day. I mean, a common neural network has at least 100 million parameters for image classification. So compared to that, I would say additional cost of, let's say, 1,000 more cycles in each round is not that much.
Yeah, hard to even measure, really.
Yes, you would practically ignore that, actually.
Well, what's next in your research? Is this an open door or the end of a long chain of events?
Oh, no, it has just begun because in our research, we have laid down this theory where we assume faultiness to be malicious. We say if a node is faulty, let's just assume the worst case scenario that it's faulty in a way that no one can control. However, in practice, maliciousness can be only so much. You cannot be arbitrarily malicious. You are restrained, and there are certain constraints on the type of attacks that a node can launch. So it would be interesting in future to combine our work with something known as fault detection techniques. So there are these fault detectors used in modern day internet where, what they do is they try to detect malicious nodes. Just for example, I know this about Facebook. Let's say a user on Facebook is incessantly, just switching from checking out like profiles after profiles after profiles, just not spending too much time on it. He's just browsing through profiles. So the Facebook server goes, and who's analyzing the activity goes like, yeah, perhaps you are not a genuine human, perhaps you are a robot, so I'm going to lock your account. These kind of things will help us control the faultiness of the nodes. And it would be practically very interesting to study fault tolerance in distributed machine learning with controlled faulty agents, because no one can be arbitrarily faulty. I mean, even in society, there are criminal activities, but those criminal activities are within some constraints. We all know that humans cannot fly, at least so far. If a bank is getting robbed and the police wants to catch the thieves, they would not set up barricades in air. They would set up barricades on the road, utilize their resources in a clever way. And this is exactly what we want to do in our research. Right now, what we are saying is we have no idea what kind of faults can be exhibited by faulty agents or faulty nodes in the network. However, in practice, we can have an idea on what kind of faults can be injected. And using that experience, let's say from people who work in this area, like what kind of faults have they seen in the past, what kind of faults are more frequent, we can fine tune our algorithm in a way that it's practically more useful, practically more efficient, perhaps bring down that CPU time that I was talking about, and perhaps even increase the fault tolerance ability. Perhaps when we assume the faults to be arbitrarily faulty, we give you a guarantee of saying that, yes, with arbitrary faults, you can tolerate, let's say, up to 20% of faulty agents in your network. However, in a controlled, constrained fault setting, that guarantee may come up to, let's say, 30%. We could say, okay, with these controlled, constrained fault behaviors, you can tolerate up to 30% of the faults.
Well, I'm going to ask listeners to grab a pen or get a new tab open in a browser, because I know there's an upcoming online event we were talking about briefly before the show. Can you share some details if people want to learn even more about your work?
So my co-author, Professor Nitin Vaidya, is organizing this tutorial on distributed optimization and learning, where he would be talking about these particular challenges of fault tolerance and security. He would, in fact, also talk about privacy challenges in distributed learning. And the tutorial is going to be a 6-hour tutorial. It's scheduled for 3 days, March 12, 19, and March 26. Each day is going to be a 2-hour session from 1 p.m. to 3 p.m. And it's going to be a virtual event whose details will be made available.
Yeah, we'll have a link to the registration in the show notes. So if any of those dates, March 12th, 19th, or 26th, people can go and sign up. Well, this has been great. Is there anything else you want to touch on before I went into a wrap-up?
If people are interested in this particular kind of problem, try Googling Byzantine Fault-Tolerance in distributed optimization and learning, or simply just learning, and you will find all this work in recent years that has appeared in all these prominent machine learning conferences and distributed community conferences that you may find very interesting. And all these works provide you both theoretical aspect of the problem and the practical aspect of the problem. They provide you with experiments. They provide all kinds of experiences of companies who have been trying to implement these systems. In fact, recently, Google gave us a grant on this particular problem of secure and private distributed machine learning. And if you have heard of this organization called Army Research Lab, they have recently announced this multi-million-dollar project with multiple universities. It's called IOBT. It stands for Internet of Battlefield Things. So Internet of Things, but they specifically deal with Internet of Battlefield Things. So they specifically deal with such adversarial nodes in networks that Army deals with when they have operations or missions within US or outside US. It's gaining a lot of attention, and for good reasons, because in recent years we have seen multiple cases where foreign malicious nodes have been able to enter your secure or or a network that you thought was secure and have been able to disrupt the algorithms or your specific tasks being performed on that network. So cyber warfare is real. Just one final note. So when we talk of cybersecurity, we are mostly thinking of preventing such kind of attacks. And when we talk about fault tolerance, we think of an additional layer of security in addition to cybersecurity measures. Meaning, yes, it would be best if no one attacks our network, but fault tolerance is a step forward where we say, okay, it's like now we have entered the damage control mode. The network has been breached, and now how can we minimize the damage? And that is all fault tolerance is about, is minimizing the damage when the system has been compromised.
Well, a very fascinating area with a lot of opportunity, I think, for a young academic looking for a place to get into some active research.
Yes, this is indeed the fastest upcoming field that I'm seeing in distributed machine learning.
Well, it'll be good to follow. Well, thank you so much for coming on the show to share your expertise and your work. This is really interesting.
Thank you very much for having me.
That concludes this installment of Data Skeptic Consensus. Our guest today was Nirupam Gupta. Claudia Armbruster is our associate producer, Vanessa Bursiaga does guest coordination, and I've been your host, Kyle Polich.